So, did anyone graph this? You finished it? Are you the only one that finished? What?
It's one.
One. This should all be on one.
Oh, okay. It's okay.
Oh. Did anyone graph all this at one? It's a piecewise function. Remember whenever we do this bracket thing, because I needed to graph them all at once.
Yeah, we did.
Did anyone graph it all at once? Here? Nope. No.
It's small?
Well, you put them all on one now?
Yeah.
Nope. Anyone else? I checked yours already. All right, is that it? Okay, who did I say got it right? You two. Did anyone else? Or just you two? You three. Okay. I'll give you 5 extra points on the quiz.
Are you kidding?
Huh?
Are you joking?
No, I'm not joking.
Like for what?
I'm giving you 5 extra points on the quiz.
Okay.
Okay, so Andy. I thought I would have gotten it. Yeah, no. Alright. What's your name? That was it, right? Just the three of you? Okay. So we'll actually come back to that. I'm not going to use it now, but later on we're going to use this for an example. So those of you who didn't get it, you can try again, and then you'll see if you're actually right when we actually go back to that in class. So let's pick up where we left off with a lot of definitions. Continues. Yes, you have a question? Yes. Yes, 1.2 definitely will be done today. Maybe also 1.3, but I don't think I'll finish 1.4. We'll see how it goes.
I want the homework today.
Oh yeah, 1.1 was due today, right? Any questions on 1.1?
Yeah, I don't know.
No.
You said there is coming down.
Do you want one?
No, but you said there was. That's coming.
No, I didn't say it. There's a quiz tomorrow. There's a quiz tomorrow. Not today. Yeah, so let's actually do that first. Questions on 1.1.
We go over 29.
So then now we won't finish 1.3. Because I forgot. It totally slipped my mind at the actually. Which one?
7.
20, 23?
29.
So we want to do 7, we want to do 29. Okay, what does 7 say?
Oh, the domain and range, so there's a graph.
Domain and range of the graph?
Yeah, because this was the same problem on the other side, and I got it wrong. for some
Oh,
reason.
what does the function? What is the function?
There's no function, it's a graph.
Oh, it gave you a picture? Draw it? I don't know if I can trust the graphs from this class. Like 3 people out of the whole class got that one right. Oh, you have the book. All right, cool. 1.1. Is the questions. All right, question 7. So they ask you to determine whether the curve is the graph of a function of x, if it is, state the domain and range. So 1, 2, 3. The top of this is around 3. This guy here is around 2.5. This guy in this line, that's around -2. The end is around -2 -3. This end point is around 2. Okay, is it a function? Yes. It's a function. How do we know?
The vertical line.
Because you just do the vertical line test. You can check anywhere you draw a vertical line, it will only touch the function once. Even on this part here. Notice that you'll cut through both these guys, but this guy is actually not there, right? It's a hole. So you actually touch the function at one point, which is this point. Right? So it is a function. What's the domain?
Square bracket.
Bracket,
Square bracket,
-2 bracket.
-3, 2. Right? Square bracket. You're looking at all x values that are accounted.
No, it's not square bracket. No, it's true.
No, it's square bracket. This is actually filled in. That's actually filled in. So it does fit the 2. Exactly. Yes?
If there's if a photograph is a line, is a vertical line, does that count as a function?
If any part is a vertical line, then no. Yeah. Any function that does something like this, and this is exactly vertical, cannot be a function. Because it means you can draw a vertical line that completely overlaps the function, and it will intersect it at an infinite number of points. Right? What's the range of that?
Professor,
Yeah?
for the domain in web design, in the web design, I put it as a square bracket -3, comma -2.
-2?
Yeah.
No, that would be wrong.
Yeah, no, but I show you what's correct.
What is accepted?
Yeah.
I put the big.
WebAssign changes the numbers. Not everyone gets the same numbers. WebAssign will change the numbers.
No, but I'm saying, regardless of the numbers, what I put is, let's just say those are the numbers.
Yeah.
I put a bracket -3, comma -2, in parentheses, then union, bracket -2, comma.
Oh, you put bracket -3, comma, -2,
Parentheses.
like this?
Okay,
Okay.
and then union, -2, and then the bracket, and then 2.
Same thing.
It's actually the same thing,
That would work, though.
but I don't know if WebAssign would recognize it.
Yeah,
But it's actually the same. Does it recognize it?
Yeah.
It's the same thing. Because here, notice you didn't include the -2, but here you did. So you sort of bridge the gap. So, I mean, there's really no, this is just a long-winded way to write the answer. It's actually the same as writing that. Right? Because the point that you miss here, you pick it up there. So, The range was, I didn't put this was 1, 2, 3. So this guy here is at -3. The gap to this on the circle here is -2. This one here is -1. Okay, what's the range?
So it's a square bracket -3, comma -2, in parentheses, union, square bracket -1, comma 2.5.
Nope, 3.
3 is 3.
Because you actually have y values past 2.5. All of these are above 2.5, and you're still at the function. The function goes up to a maximum point of 3.
So you want to look at the, oh, you're looking for the range.
Yeah, all possible y values that give you
But
a
the
answer.
sign has accepted 2.5.
That's wrong, unless they change the numbers on me. This would be 3. So yeah, notice that the things might look similar, but Weberstein will actually change the numbers in the problem sometimes. We look at 29. Find the domain. F of x is equal to, well, it says h of x. Okay, how do we do this one?
We can factor x. And then
What are the requirements?
X has to be positive.
X squared minus 5 is actually positive.
yeah.
Right, so our restrictions here. 1 for the radical. You need that x squared minus 5x must be greater than or equal to 0. For the rational function. Oh, I didn't tell you what a rational function was. Let's describe it as the denominator. You need that the x squared minus 5x not be 0. Which both of these combined simply means you need x squared minus 5x to be greater than 0. Right? So that's the restriction you have to fulfill. How do we know where is x squared minus 5x greater than 0?
First factor of the x.
You factor it. From these to be equal to 0, you get two solutions. You get x equals 0, here gives you x equals 5. And you're going to have to test the intervals, right? So all the way going down here, there's infinity. All the way going back here is minus infinity. And now we want to test the region. It's sufficient to test only one point in each region because they'll all behave the same. So you can test, say, -1, and you plug it into that function, right? You get -1 times -6. Negative times negative is positive. So yes, this interval works. Plug in a number between here, 1. You get 1 times -4. Positive times negative is negative. You want it to be positive, so this does not work. Plug in a number over here, that's 6. You get 6 times 1, which is positive times positive is positive. And so over here works. And so these two intervals work. You have strict inequality, so these cannot be included, right? So the only thing that works is here and here, which means the domain H is minus infinity up to 0, not including 0, union 5. Yes?
It's not part of the question, but how different would the answer be if it was the third root of that instead of the fourth root? How different the answer would be?
This would be your only restriction. Because with odd roots, if you have an odd number here, the radical works whether it's positive or negative.
So that would be your
So you won't need greater than or equal to 0. You won't need an inequality. It will just be don't be 0. So it will be only the points 0 and 5 don't work, but everything else does. So your interval would look like minus infinity to 0, union 0 to 5, union 5 to infinity, where 0 and 5 are not included. Right. For odd roots, this is not a requirement. This is only a requirement for even roots. Yes?
Without doing all that, the factor and everything, you just, well, you have the factoring, so you just plug in numbers to that, x squared minus 5x. Can you say restriction is non-negative radical?
No. And that way is actually not a good way, because how do you know what numbers you want to test? Right?
No, yeah, I mean, like, yeah, getting the x equals 0, x equals 5, but then plugging those into x squared minus 5x instead.
Plugging in these specific values?
No. Like, the way you just did it, like testing one number of each,
Yeah.
but putting in x squared minus 5x. Like grabbing -1 and putting in -1 squared.
Oh, putting it in here and here are the same thing. It's actually the same thing, I just found. I like plugging into the factored form though, because it's easy to see like positive times negative or negative times positive. Whereas here, if you plug it in, more than likely you have to work it out. Let's say, you have to plug in 6 squared and actually minus 5 times 6, and then you have 36 minus 30. Right? This would require a lot more arithmetic than this one. Here, I don't even care what the numbers are. I just want to see positive versus negative. Right? Clearly, if x is bigger than 5, this is positive. If x is less than 5, it's negative. It's easy to just see that right away. I don't need to know what the numbers are. I don't care, as long as it's bigger than 0. So in general, if you're testing functions, I would test in the factored form. It's less arithmetic. Other questions?
For numbers 39 to 40, how do you show your work when you find the
Oh, you just do it individually. So
you just sketch the graph and write your domain?
yeah, you just write it down. So you sketch the graph, you'll get a sketch like this, and you can say, oh, from the picture. But in general, I wouldn't ask you from the picture. Like I'm not gonna, like, especially in this section, I wouldn't ask you to graph things much. So if you see something like 39, you can actually know what the domain is without graphing the picture. And that's by just looking at the domain of the pieces. So this is if x is less than 0, x is greater than or equal to 0. Notice that both of these are polynomials. So any x will work. In particular, any x less than 0 will work. And here, any x greater than or equal to 0 will work. They're polynomials. I can plug in anything I want. Right? And because less than 0 and greater than or equal to 0 covers every number on the real line, the domain here is just minus infinity to infinity. Because anything will work. If you had something like one of those things, 2 for x greater than 1, and of course, here your x cannot be 2, right? And then something like x squared for x less than or equal to 1. In that case, you can look at this and know that 2 is not in the domain. This guy, anything will work, but this guy, not anything will work. The 2 can actually won't work. So the domain here, since this guy provides no restriction, I can plug in anything. The only restriction I care about is this guy. And so the domain here will be minus infinity up to 2, union 2 to infinity. Right? And I didn't have to draw the picture. Just knowing how the function itself behaves was good enough.
But it says the sketch is right.
Yeah, of course, if it asks you to sketch it, you should sketch it. But know how to know without sketching it, because in general, I won't ask you to sketch something like that.
Oh, I didn't know how to sketch the graph volume based on the absolute values. I didn't know how to do that.
That was on what?
Okay, now this comes from knowing the properties of absolute value of x. 37. Recall absolute absolute value of x is equal to what?
Positive absolute x.
It's x if x is greater than or equal to 0, and it's minus x if x is less than 0, right?
Yeah.
So if I have absolute value x over x, what is that equal to?
Could be 1 or maybe 1.
Right, it's x over x, which is 1, provided that your x is greater than or equal to 0, or it's minus x over x equals negative 1, provided your x is less than 0. So this guy actually looks like, on the right side of the y-axis, it's 1. On the left side, it's minus 1. So, if you're looking at now, they ask you about
3x.
3x plus absolute value of x over x. I would probably just think of this as 3x over x plus absolute value of x over x, which is 3 plus absolute value of x over x. And so you just know that this is actually 3 plus 1 when your x is greater than or equal to 0, and it's 3 minus 1 when your x is less than 0 by this. So then it's actually, so the graph would actually look like it's 4 when you're positive, and it will be 2 when you're negative. So that would be the picture. Right, but it comes from knowing absolute value.
Where do you get the greater than or equal to sign? How is that defined? Greater than or equal to?
You can actually put this on either one. Either one is fine. I just go by this because it's the definition. Absolute value of 0 is 0. So.
But in this problem, we both have the open circles, right?
Yes, because the x on the denominator. So
Yeah, that's what I was going to do.
yeah, sorry, that's fine.
You still have the equal sign.
Yes. We can be equal to 0 because there was an x in the denominator.
Yeah.
Right. Is that it? Okay, you can pass the homework up. Just pass it in front of you until I get to it. Okay, so now we're ready to move on. So I spoke about polynomials, coefficients, degrees, linear, quadratic, cubic. Yeah, third degree polynomial. Next function we want to look at are power functions. So the first type is things that look like this, where n is a positive integer. You should know that the graph is a parabola if n is even, and it actually looks like a cubic if n is odd. And the only thing that changes is the bigger the power is, the wider the graph seems. So, like if y equals x squared would look like this, while if you have y equals x to the fourth, it would look a little broader, right? Or if you have y equals x cubed, it looks like this. Get y equals x to the fifth. to look a little broader. Right? So the higher the power, the longer it takes to do what it's doing. But in general, that's what you need to know. And so when n is even, you know both n's go up towards infinity. And if n is odd, both n's go towards this, right? And if the coefficient is negative, the thing will flip upside down. If you have minus x to the n, then if n is even, it will actually look like a parabola going upside down. If n is odd, like a parabola going up. Sorry. You would look like the upside down version of the other one. For now, knowing how the graph behaves is enough for us. It's going to give us the intuition that we need. So when there's a negative sign, just have the same sort of behavior, except everything's flipped upside down. There's also the second type of power function, 1 over n, where n is integer. These give you radicals, right? X to the 1 over n. We learned from algebra class that this is just the nth root of x, right? So it's just radicals. So if n is even, it will look like this. If n is odd, it looks sort of like this. And of course the negatives flip things upside down. Right, so notice here when n is even, you require that your x has to be greater than or equal to 0 and x is anything. The third kind of power function is the reciprocal function. So it's x to the minus 1. You can even do this in general. Your book talks about x to the minus 1, but x to the minus is more general. N is a positive integer. So let's do x to the minus 1 as a special case, because it's something you should know what that looks like right away. The graph will look like this. X equals 0 is a vertical asymptote, y equals 0 is a horizontal asymptote. And in general, you have x to the minus n, then if your n is odd, it will look sort of like that. If your n is even, right? So 1 over x squared looks like this. 1 over x to the 4th looks like this. 1 over x to the 6th looks like this. And so these guys are like x to the minus 1, x to the minus 3, x to the minus 5, etc. These guys are x to the minus 2, x to the minus 4, x to the minus 6, etc. And notice that x equals 0 is never in the domain. range cannot be zero, right? It can have negative infinity up to 0, and then from 0 to infinity, or just greater than 0, depending on what you have. But 0 cannot be in the domain or the range. Some nice facts. Have you guys seen all these kinds of functions before? This is supposed to be like a review, the first 2 sections. So hopefully you've seen this before. What are rational functions? What do they look like? Fractions? What kind of functions can appear in the fraction? 1 over radical x?
Negatives.
That's not They have to be polynomials. So r of x is a rational function. Means r of x equals p of x over q of x, where q of x is never 0, and p of x and q of x are polynomials. And the graph for those can vary very greatly, but in a pre-calculus class you'd graph all sorts of rational functions. And we are going to get to a section called curve sketching where we're going to again graph a whole bunch of rational functions. And we're going to do it in far more detail than you could in a pre-calculus class because we're going to have better tools at our disposal. But for now, that's all you need to know. Trig functions. The main ones. Sin x and cosine x. What's the domain for sin x and cosine x? Everything. Anything you plug into these functions will work. They also have the same range. What's the range for both?
So 1 and -1.
-1 to 1 inclusive. Right? So in particular, sin x is always between 1 and -1. That's going to help us a lot down the road. The same is true for cosine x. Always true. So if you ever write down on a paper sin x equals 5, I'm just going to ignore everything you say. Well, it is nice to know the graphs, but I actually drew those before in class, so I won't go over that. Other ones. Who remembers how sin x and cosine x were formed? What is sin x and cosine x? Well, that's actually a consequence of their definition. Where do they come from originally? Nope.
Circle.
They come from the circle. What's their relationship to the circle?
Sin is like the y.
That is correct. They give you the coordinates on the unit circle. This would be cosine theta, sine theta, provided that the line connected to the origin makes an angle of theta with the positive x-axis. Right? So these actually give you the coordinates on the unit circle. The whole triangle business came from doing that. The triangle came after the circle. But yeah, mathematicians wanted a way to map how you get points on a circle. These were the two functions that did it. And because it's the unit circle, that's why they can never pass 1 or minus 1. Right? But the angle can keep winding around forever, and that's why their domain is anything. The angle can be anything. Other trig functions. Other things about sine and cosine that you should know at a glance. If you have sine x equal to 0, this means that x equals what? Well, sine x is equal to 0 where? Everywhere here and everywhere here, right? No, here and here, right? Where the y equals 0.
Or 180.
So this would be 0, 2 pi, 4 pi, 6 pi, 8 pi. This would be pi, 3 pi, 5 pi, blah, blah, blah. In other words, any multiple of pi. And if you're given a restriction, you just choose the ends you want. So if they say, oh, we only want all the answers between 0 and 2 pi, obviously the end would be 0, 1, and 2. Right? Cosine is equal to 0 where?
90.
N pi over 2, where n is an odd integer. So power 2, 3 power 2, 5 power 2, 7 power 2, etc. Sine x equals 1 where?
N over 2 pi where n is
And what?
where n is odd.
N pi over 2 where n is what?
Odd.
No.
Pi over n where n is
Positive, wait.
Because at pi over 2 sine is 1, but at 3 pi over 2 it's minus 1. So you sort of skip it. Right? So n is like 1 and 5. So you have to skip some. It goes by fours. Cosine x equals 1 is easier.
Professor, what it says, n equals 1, comma 5?
Yeah.
You keep skipping.
1, 5, 9. Go by fours. Cosine is 1 where? 0, 2 pi, 4 pi, 6 pi. So what's the formula? N pi, what's n? Has to be an even number. So this is how in depth I need you to know sine and cosine, not just the graphs. You need to know their properties when it hits certain values, like 0 and 1, and of course all the other nice ones like a half, radical 3 over 2, all that stuff. Radical 2 over 2. Which, by the way, I should probably write that down. The easiest way I find to remember this is to do a little table where you count up by the degrees, 30 degrees, 45 degrees, 60 degrees. This is pi over 6, this is pi over 4, this is pi over 3. Right? Right. How you fill out the table is for sine, you count up from 1 to 3. Go backwards with cosine. Take the radical of everybody. Radical 1 is 1. Then you divide by 2. Right? So now you know sine of pi over 6 is a half, cosine of pi over 4 is radical 2 over 2. You sort of have this table in your head, it's easy to fill out. It's just 1, 2, 3 going from left to right. Easy to figure out. So yeah, when I gave you those problems on the quiz, like sine of 5 pi over 6, I expected that to only take you a few seconds to figure out who you mistake. When you have, say, sine of 5 pi over 6, something like that. Whenever you have a special angle involved, you sort of see that guy sticking out at you, and then you try to take that many pieces. So what happens with sine pi over 6 is you take pi and you divide into 6 pieces, right? Because it's pi over 6. And you go the other way. You need 5 pieces of pi over 6, so you count off 5. Right? So you know you're in the second quadrant. Which means sine is positive because we know all students take calculus. And so this means that sine 5 pi over 6 is the positive sine of pi over 6. Right? It just takes the value of the special angle. So you know sine pi over 6 in the table in your head, pi over 6 you know is on the left, sine goes 1, 2, 3, so this has to be a half. Right? And of course I expect you to know the graphs. Something else, a function called the tangent. What's its definition?
Sine over cosine.
Sine over cosine. This implies the domain of tangent is what?
It's
All x such that what?
Cosine theta is not 0.
Cosine theta is not 0. All of theta. But where is cosine theta equal to 0? N pi over 2, where n is odd. Right? We also have secant theta, which is 1 over cosine theta. So again, that domain cannot include those. We have cosecant theta, which is 1 over sine. You have cotangent theta, which is 1 over tangent, which you can think of as cosine over sine. So the domain of that does not include n pi for n is in the integer. The next function we talked about in this section is exponential functions and log functions, but that's actually not in our syllabus. You're gonna deal with those in detail in chapter 5, which is where calculus 2 starts. So we're going up to chapter 4.
So what does it say? The all theta for 10.
Again?
Right there. All theta was the
All such that. That's my shorthand for such that. Okay, so we're skipping exponential and logs. More review, transformations. How to get new graphs from old graphs so you don't have to be sitting there plotting points like you're in pre-calc. Or, no, not even pre-calc, algebra. It's going to be very important for you to sort of know how a function looks very quickly without going through a lot of trouble. Because otherwise your life will be really hard in this class. In other words, you don't have time to plot points, right? When someone gives you an exam and they say this is the time, they're not thinking, oh, he's going to need time to plot points. It's just not time they're going to be given, right? So you have to be really quickly be able to draw these graphs. So transformations. And so you learn about transformations mostly in pre-calc, I think. So some of the main ones are given f of x. If you see and c greater than 0, then if I say f of x plus c, what does that do to the graph of f of x?
Moves it up. Yeah, up.
This graph up c units, right? If I have f of x minus c, it
Down.
shifts graph down by c units. So if we know that y equals x squared, looks like this, then when I ask you about y equals x squared plus 1, I expect you to know it's that same graph, you just shifted up 1. Right? I don't expect you to start plugging in numbers. Right? You should also know that y equals x squared minus 1. This means you shifted down 1. Right? So you see this should immediately pop in your head. I don't expect you to be plotting points. If you have f of x minus c,
To the right. To the right.
Right, we'll do
right, shift to the right by c units. And if you have f of x plus c,
Left.
shift to the left by c units. So again, if I have y equals x minus 1 all squared, I don't expect you to plot points, I just expect you to know that just shifts the guy to the right. So now this is at 1. Right? Y equals x plus 1 squared, well that just shifts the guy to the left, to minus 1. Right? Stretching. So if I have now f of x, a function c greater than 1, then things like c times f of x, or 1 over c f of x, or f of cx, f of c over c, f of minus x minus f of x. This is the last thing in the section. Okay, so
Stretch vertically, the first one.
this stretches vertically by c factor c. This shrinks vertically. This guy, what does this one do when it's multiplying this? This shrinks. Right? The x sort of behaves in the opposite way that you think it might. Shrinks horizontally by factor c. This stretches horizontally by c. Right? The reason being, for example, for a function like this here, x has to be bigger in order to get to the same point. Right? So if this was, say, a 5 here, your x would have to be 5 before it gets to f of 1, whereas before it only had to go to 1. Right? So it has to stretch it out a lot longer. Right? This one, what does this do?
Reflects on the x-axis.
In which axis?
Y-axis.
The y-axis. This one
X.
reflects in x-axis. So again, if your y equals x squared, let's say it looks like this, then y equals 2x squared, it would look a lot skinnier, right? Because when you're over here, you only rise this much, but when you're there, you rise even higher, right? Your y value gets higher, so it seems to like stretch it vertically. If your y is equal to x squared over 2, then it becomes what? Or this is y equals we put minus x squared. That means the minus is in front of the f of x. You're reflecting the x-axis, which is the horizontal axis, and that's why you get this guy. Reflecting in the y-axis, that's x squared is actually not a good example for that. Maybe x cubed. If y equals x cubed, this looks like this. Y equals minus x cubed, which is just f of minus x. It would flip in the y-axis. So it would look like that. And of course, you can combine several of these at the same time, right? So you can apply several transformations at the same time. Example, if I wanted to graph 2x minus 1 squared plus 3, you shouldn't have to expand and then factor and try to figure stuff like that out. You just know that.
You move to the right and move up the
Right? You just start with a graph of x squared. This tells you to shift it 1 unit to the right. The 2 is just going to stretch it vertically. And then the 3 says you move it up 3. So you know the graph of this is going to look like that, where this is at the level of 3. Right? If you want to figure out what this guy is, you just plug in x equals 0 and solve for y. Right? Like that's in general. The x-intercept, we set y equal to 0, solve for x. The y-intercept set x equals 0, solve for y. So I expect you to remember all that. Yes?
Is this supposed to be like when?
Come again?
Is it supposed to be like
Stretch.
Well, yeah, it's supposed to stretch, but well, probably you don't really see it. It's a sketch. It's not. I mean, the 2 wasn't there. I mean, I draw it a little like narrower, but probably wouldn't use it. It's just one of these. It's subjective to say it stretches. That's not wide enough. Like it says who? It's a sketch. You know, it's not like I'm like on a graph paper or anything. You know. Yeah.
What if you wanted to reflect it over the origin? Would that be a combination of x and y axis, or would you have to like do random?
Yeah, you reflect over the y and then over the x. That's what we call reflecting over the origin.
Can't you see that? No, I mean, you have to go like this and this, or just like that.
I find it's easier to think of it that way than to do it straight that way. Like I feel like a lot of people make mistakes when they just do it. Oh yeah, just switch around, you know, they tend to mess up. Yeah, what else? Composite functions. Everyone loves composite functions.
No, yeah.
Those are going to be super important. Very, very important. What are composite functions? Basically, think of them as functions of functions. Right? You plug in a function into a function, you get what you call a composite function. Example, f of g of x, right? Where the input is another function. And we have the notation f of g of x, like how I expressed it on the quiz was f circle g of x. Right, you draw a circle, not a dot. The dot will be multiplied. Right, you literally draw a little circle. It means the same thing. The principle behind that is just doing evaluation. Right, so for example, if I say f of x equals 2x squared plus 3x plus 1, then if I ask you what is f of 1, right? What is that? You plug in 1 for all the x. Whenever you see an x, you put a 1.
6.
Right? That's just 6, right? If I say f of 2, plug in 2.
8.
Right? If I say f of smiley face,
You put the
what do you do?
smiley face.
Confused. Okay, you just say 2 smiley face squared plus 3 smiley face plus 1. And of course, smiley face is in the domain of every function. Right? So whatever shows up here, I don't care what it looks like, how complicated it is, you put it everywhere you see an x. Right? So if I come and I say g of x is the function 3x plus 1, and I ask you what is f of g of x. What does that mean? Well, that just means f of 3x plus 1, and you follow the same rule. Whatever shows up in brackets here, you replace every instance of x with it. That's going to just be 2, 3x plus 1 squared plus 3, 3x plus 1.
Do you want us to leave it like that, or do you want us to solve it?
In general, I want you to expand and simplify. It's going to be important in chapter 2 to go all over. Right? So that's what you do, and then you simplify. So if I say something like f of x plus h, what do you do?
2 times.
What does 2x plus h squared plus
3 times x plus h plus 1.
Right. Notice that this is not the same as just saying 2x squared plus 3x plus 1 and then plus h. It's not the same thing. A lot of people do that. Even on the quiz, a lot of people did that. This is actually equal to f of x plus h separately. It's not the same thing. I can know when people do that because I often ask you to find f of x plus h minus f of x over h, right? And if you do this, the answer will always be 1, no matter what the function is. So anytime I say you want to write 1, I know, oh yeah, we did that. What would this look like for that function?
You put it.
First, you plug in f of x plus h.
Right, so you look at the function, everywhere you see an x, you put an x plus h, right? So this is 2x plus h squared plus 3x plus h plus 1 minus
The original 2x.
We don't have minus.
Yeah.
Oh, yeah, for that.
2x
bracket
2x squared plus 3x.
or parentheses, whatever you want.
2x
2x squared plus 3x plus 1 all over h. This is 2, what is this quickly?
X squared.
I don't expect it to be writing x plus h times x plus h for no. You know that as soon as you see it, you know that. Plus 3x plus 3h plus 1 minus 2x squared minus 3x minus 1. Without the brackets, you would have right?
And then you
Now
add
notice the 2x squared is going to kill that.
the 3x also.
This is going to kill that. The ones are going to die as well. You're going to end up with 4xh plus 2h squared plus 3h all over h.
Factor of h.
Factor of h.
Yeah, you're done.
X times x plus h plus 3.
Just cancel.
Oh. That's it. That's it.
That would be the answer. In chapter 2, this is actually, you see this all the time. In pre-calc, they were even asking about this guy. It's actually a very important function. And in chapter 2, we'll see why this particular composite function is very important.
That's the limit, the original limit.
Yeah, like that guy's responsible for like half of all calculus. It's a really important function. It's called the difference function. I think we'll stop there. That ends 1.2. Homework for that is due tomorrow.